Hey, welcome back once again. Inductor is like Hulk. It has very good application, but it is very hard to control. Last time we saw different modes by which the avalanche breakdown occurs in a MOSFET due to this inductor. This time we'll see the avalanche ruggedness. There are two types of avalanche ruggedness that occur in a MOSFET circuitry. Let's see those in this video. The two types of avalanche ruggedness are single shot avalanche ruggedness and repetitive avalanche ruggedness. Let's see a simple circuit of a MOSFET driving an inductor, which might create avalanche energy or current in the system. The single shot, or also known as single pulse avalanche ruggedness, is an event which can generate significant avalanche current and or energy during MOSFET switching application when there is an inductive load. When the energy and current generated by this event are low, the impact on the MOSFET is very negligible. It can sustain that and discharge the inductor easily. However, if the inductor value is high, due to that there is high induced flyback voltage, and because of that the avalanche induces either high energies or high currents in the MOSFET. Then it can be destroyed. We saw last time how an avalanche breakdown occurred in a MOSFET. If you haven't seen that video, please click on this card above. To see more such videos, please subscribe to our channel. Well, energy is not the real issue here. The current and temperature are the real culprits. So the avalanche event occurs in such a short time period that the heat doesn't have time to be transferred to the PCB on which the MOSFET is mounted. We'll see the waveforms of the circuit behavior to understand this in a better way. Here we'll see the gate to source voltage, the current flowing through the inductor, drain to source voltage of the MOSFET, peak drain current to source avalanche power of the MOSFET, and junction temperature rise during the avalanche effect. At time T0 to T1, the MOSFET is off. There will be no current flowing to the MOSFET. The drain to source voltage of the MOSFET will be equal to the supply voltage. Now we turn on the MOSFET at time T1 by increasing the gate to source voltage. Once the MOSFET is fully on, the current starts flowing to the circuit and we start charging this inductor. So the current through the inductor starts increasing gradually, which stores the electromagnetic energy. The drain to source voltage of the MOSFET falls down and it becomes very low, around close to zero value. Here the inductor is fully charged and reaches the peak current. We turn off the MOSFET at time T2 by removing the gate to source voltage and current is cut off. But this inductor opposes the change in circuit current. It wants to keep the current in the same direction. So at this point, the inductor induces a flyback voltage which adds up with the supply voltage and the drain to source voltage increases, which is obviously above the supply voltage. This voltage stays at the same level until the inductor discharges and full current flows out of it. The time period required to fully discharge this inductor is called as avalanche time. If we see the power across the device, which can be calculated with simple multiplication of current and voltage. During an avalanche event, when the MOSFET turns off, this power reaches at its peak value and decreases as the current flowing through the circuit decreases, which discharges the inductor. This power dissipates across the MOSFET, and because of this, the device heats up pretty much. So the temperature across the MOSFET rises tremendously. We need to make sure this temperature rise in the MOSFET should be within the junction temperature limit. If the temperature of the MOSFET goes beyond that, it will fry like a chicken on a barbecue. So we can calculate this rise in junction temperature using this formula. This shows the power flowing to the device, and this is the MOSFET's transient thermal impedance, which is mentioned in the datasheet. Once we calculate the rise in junction temperature in the MOSFET, then we can add this to the ambient or the junction temperature of the MOSFET prior to the turn-off process. Well, that is the lengthy process. Fortunately, to make this process more simpler, the avalanche rating graph is present in every MOSFET datasheet, which is also known as Avalanche Safe Operating Area, which shows how much will be the junction temperature of the MOSFET against the peak avalanche current flowing through this MOSFET, and for how much time this current is flowing through it, which is also known as avalanche time. As we can see, the drain to source voltage on the MOSFET increases with a remarkable rate, and our MOSFET should handle this drain to source voltage. It should not go under breakdown. So generally, the breakdown voltage of any MOSFET is 1.3 times of its actual VDS rating. For example, if there is a 60 volt MOSFET, then its breakdown voltage will be around 78 volts. One more important thing is that the longer the avalanche time is, the less avalanche current capability of the MOSFET will be. This avalanche rating graph shows the avalanche ruggedness of the MOSFET. If you see, there are multiple lines on this graph based on the junction temperature of the MOSFET, which are generally denoted for 25 degrees Celsius and 150 degrees Celsius junction temperature of the MOSFET. As the temperature increases, the avalanche ruggedness of MOSFET decreases. And this line over here represents the repetitive avalanche. Well, what is a repetitive avalanche? Generally, for high switching applications, MOSFET turns on and off continuously. If we apply the same principle and check the gate to source voltage, inductor current, and drain to source voltage of the MOSFET in this case to understand, the gate to source voltage will turn on and turn off continuously. When the MOSFET is on, the current flowing through the circuit will rise up, charging the inductor up to peak current. When we switch out the MOSFET, the current will decrease, discharging the energy stored in the inductor. At this point, we get the voltage overshoot across the MOSFET, and it stays over there up to the avalanche time and goes back down to the supply voltage. This process keeps on repeating, and we see the avalanche power and change in junction temperature of the MOSFET each switching cycle, and this is called repetitive avalanche. In the repetitive avalanche also, we need to consider junction temperature and avalanche current. But that's not it. The number of cycles in which this avalanche is occurring should not exceed the avalanche cycle limit of the MOSFET. We have to consider the cooling of the MOSFET in each cycle when it goes to avalanche. The limit of a MOSFET's number of avalanche cycles can be determined through a second chart, which is mentioned in some of the MOSFET datasheet with the number of events. So, power MOSFET can sustain through a single shot avalanche event and repetitive avalanche events if it is operated under safe operating area. This avalanche occurs in many applications like power steering of a car, horns, and many motor applications. Well, that's all about the inductive load switching a MOSFET. Next time we'll see something new. Till then, stay tuned. I've added all the reference on this topic in the description. I hope you got something from this. If you haven't, you can watch the video again. Still, if you don't, you can ask your doubts in the comment box below. Hit the like button if you like this video, subscribe to my channel, and finally, thanks for watching.